Yeah, sounds good. So I'm actually super excited to give this talk here today. I think it's the third carry-on talk from one of the original founding members of development of the Pony programming languages. I think Sylvan Klepsch has given 2 talks before me. Who actually here in the audience is familiar with the actor programming paradigm? Great, almost anybody. And who knows about the Pony programming language? This is awesome actually, and quite unusual because almost anybody knows it here, so that's very gratifying. It's actually no secret that we are interested in actors. I think the personal story for me for the actor programming paradigm began about 10 years ago. I think it was about when Akka came out. And then I did a master's program with my supervisor, Sofia Drosopoulou, for continuing work in the actor world, and some that came out of it was parts of the Pony programming language. So just as a quick recap, what the actor programming paradigm is, you basically, it's a programming model where you have an abstract interface to active objects, and you can switch the state of those objects by sending asynchronous messages. So rather than modifying their state directly through methods, you send them messages, and then the actor themselves worry about the state switching. Now, in the original proposal from the actor paradigm, there is no shared state between actors. That is not true for all of the languages that exist implementing that paradigm, but certainly there are which totally stick to the original definition. And by employing some scheme of runtime scheduling, actors may execute concurrently in parallel, and we have seen quite some languages employing this paradigm. For example, Pony, as I've just mentioned. We have Encore, which actually share the same runtime, Pony and Encore, and we have famous languages like Erlang. We have the Akka framework. We have the C++ actor framework, Salsa, and many more. So I don't have enough space to mention all of the languages here on this slide. So. Who actually here in the audience is also familiar with distributed Pony and the fact that having distribution in Pony was always a plan, and who is desperately waiting for it? So I'm desperately waiting for it as well, since this is one of the main things I work on, and I actually want to get into the Pony language as well. But before that, my supervisor, and I'm doing a part-time PhD with her, told me that there needs to be some benchmarking around and find out which of those actor languages are most efficient, and then how will they compare for a decent set of programs or for a large set of programs. And so I embarked on the endeavor of benchmarking actor languages, because at first I thought, how hard can it be? I was just starting a decent toolchain for myself and then start benchmarking. So since I do have a background in industry, and I was lucky enough to have access to quite a good environment where I can do those benchmarks on, we had 2 machines available, one medium-sized one where we had 2 sockets and 24 cores each with hyperthreading, and we had a large machine available for testing, which was 4 sockets and 112 cores. Plus hyperthreading, and obviously we made sure for both of these setups that all of the sockets had the same amount of memory and the same kind of memory. So the environment problem was solved, and then I started thinking about how am I going to approach this, because I thought myself, how hard can it be? It's just a bit about benchmarking. So I had built myself a custom toolchain where I can just tell it which programs to run, and it will figure out everything automatically. What are the physical cores on my box? What are the logical cores on my box? It will detect NUMA node placement. It will run all of the benchmarks I told it to do so, and then produce me beautiful plots out of those runs. And there's nothing I need to worry about anymore. I just run programs, see the results, and then be able to analyze what those results will be. Now, just as a short information on how we did the measuring, we were actually measuring the time taken to complete the individual program, not until the process was terminated. And obviously the tool I was mentioning here that does all the automatic running is NUMA aware, so it will detect where on which NUMA node the core is. And then in order to measure scale factors, it will NUMA aware switch off cores and then enable them again in the order respecting NUMA placement, and will make sure that the program runs on the closest NUMA nodes. I think there was a question, yes?
For those uninitiated, what is NUMA?
NUMA is basically, it is called non-uniform memory architecture, which means that on large machines, and that's pretty much true for most of the new x86 architectures, or for the x86 architectures that have been existing for quite some time, is that you don't have uniform access to every memory bank from any of the cores you have in your CPU. So usually what you have is that you have a quick path interconnect between CPUs, and they need to have a certain communication protocol to access memory from some other bank that is owned by some other core. And that makes a performance difference on where you have your code running compared to where your data is. And what this benchmark suite is making sure of that when you run a program, for example, on one core or two cores, that those two cores will be close together and that the memory will be stored close to those cores, so that we don't suffer any of those differences between this non-uniform memory access protocols, so that we see less jitter in the benchmarks. That was at least the assumption and the original design decision that we used for that benchmarking program. Now obviously we were using two approaches on how we did the NUMA-aware benchmark running. There is a tool on Unix machines which is called NUMA control, where you can sort of tell a process on which NUMA node it is allowed to run. Or you can do the hardcore way by hardware switching of CPUs, and then the program will only be able to be scheduled by the operating system on any of the CPUs that are physically available. Now the original problem with using NUMA control and CPU offlining at the same time is that there is a confirmed Linux bug on big machines where you cannot CPU offline cores anymore, so that's why we needed to use NUMA control. But it actually was a good thing to happen, because it's quite interesting what happens to the results when you use NUMA control or CPU offlining. So then I thought, okay, I have the tool, I just need to run a program, it will plot the results, and I'm done. And I give the results to my supervisor, and everybody would be happy. And I have to say, boy, was I wrong. I thought finding the programs will not be that hard, because there is a Savina benchmark suite. There has been a publication about this, I think, 4 years ago at the Agir workshop. And it is a benchmark suite which was specifically designed for actor systems. So I was super happy. I have all the programs I need, and I have all the programs that are actor program like that I can run, and the only thing that I need to do is implement those benchmarks, in our case in Pony, and then compare the runtimes to languages like Akka, the C++, or the C++ actor framework. Now what the original designers of the Savina benchmark suite have been doing is they were providing programs in 3 categories. There is a micro category, which is designed to be very small programs that exercise individual components of a runtime system of a language, for example, scheduler performance, for example, message queue performance, and alike. And then there is a second category, which is the concurrency category, where we have entities in that actor program that are competing for a shared resource, for example, a bounded buffer, or anything you can imagine when it comes to concurrently accessing some shared information. And there is a parallelism category, which basically includes benchmark programs where you have divide and conquer style stuff, where individual computations or data processing can happen fully in parallel, and there needs to be no coordination between those actors. So in the next couple of minutes, I want to go through some of the results we are seeing for all of the individual categories. And just as a quick pre-information, I was benchmarking Pony 0280 with CAF 16.3 and Akka 232. I'm aware that the Akka version is not the newest one available, but we used the implementation from the original Savina paper on those Akka implementations, because I wanted to avoid that I am the guy implementing all of the benchmarks in all languages. I only was the guy implementing the stuff in Pony, and the CAF implementation came from the CAF team, and the Akka implementation from the original Savina paper author. So good. one of the first benchmarks that is classified in the micro group is the thread ring benchmark. What the thread ring benchmark basically does is there is a ring of actors, and every actor holds a reference to its neighbor, and they form a ring, and then a message token is passed into the ring, and the message is then forwarded to the neighbor. So what is actually the performance graph you would expect it to look like if you run that program from one core to n many cores? How do you think would that look like? Anyone?
So what are we? Do we measure? Are we trying to see? Given that many actors, how many times are we going to pass this message around?
So actually, what the benchmark does, there is n many actors in that ring, and you pass the message to the first actor, and that token will be passed around n many times.
Okay, so that's in squared passes.
Basically, yes.
Oh, okay, fair enough.
Yeah. So back to the original question with the performance graph that we would expect here. So just from a technical perspective, since the message is passed one at a time from one actor to another, there's absolutely no parallelism involved. So I wouldn't expect any scaling from 1 to n cores, and this is how the graph looks like. Now, what are the things that come into your mind when you see this graph? What are the interesting points when you look at this plot? Interesting and surprising points, yes?
Pony's awesome.
Pony's awesome, and Akka has a very big spike around 24.
Absolutely. So what we see here is that, first of all, Akka and Calf seem to improve from 1 to 2 cores, which at first seems to be hard to understand because there's no concurrency or parallelism involved. The message is passed one at a time. And we do see a big spike in Akka from 24 cores onwards. Now, the explanation for this 24 cores onwards would be, remember that we are running here on the smaller machine, is the 25th core and more is hyperthreading. So what you see here is the penalty in hyperthreading. That still doesn't explain what happens for Calf and Akka from 1 to 2 cores. My suspicion is, and I have confirmed that with the Calf developers, is that we have thread contention on 1 core. So the runtime system would spawn more threads that are available, or cores than are available, and you have thread contention on that 1 core then. And that will sort of wash out a bit when you move to 2 cores, because then they are not only contending for one scheduler queue. And the good news about Pony is it seems to flatline with some weird spike at 10 cores, which is quite interesting actually. And this story sort of also looks similar on a big box. The only difference is that Akka looks a bit different than it used to be on the smaller box. And Pony now behaves even better because it totally flatlines. There's no random spike anymore. Unfortunately, we will see in a couple of minutes that there are also some benchmarks where Pony doesn't do that well. And what we see here on the big box is that we see a pretty tough spike for Calf on 1 core here. And we will see later on that there is a difference between whether you use NUMA control or CPU offlining, which makes quite a big difference for Calf.
A question here.
Yes.
So, is there some core implementation reason that you have found for why Akka is so spiky in comparison to the other two?
So far not, but we would be happy in a discussion about that. Yes. We have the expert here, so that would be perfect. Do you have maybe an idea on what is going on here for the spikiness? Yeah?
Could it be garbage collection related maybe?
Garbage collection could be something that has to do with it, primarily because we are on the JVM here, so we have a stop the world garbage collector. And usually when you experience stop the world garbage collector, you tend to see some jitter for certain programs, certainly not for the total average case, but there are programs where you see this, and this could be a case here. Yep.
Presumably you've run the test more than once though, right? Or
yeah, absolutely. So we did.
So these spikes consistent then?
The spikes are consistent. So what we do here, I think we made 20 runs each, and then took the median of those 20 runs.
So question, I mean, I think it's important to know how many messages you're sending and like just the memory consumption, right? How many objects are you creating and
Absolutely.
allocating, deallocating, etc.
Yeah. So for the thread-wing benchmark, I think it is 50 actors that are allocated in advance forming that ring, and then that token is passed around 1,000 times. So memory-wise, it's not that tough, and that's why I would be very surprised if GC would dominate the spikiness of this program here.
I guess you already answered my question, but I was wondering if you tried different GC algorithms, because you can switch them up in the JVM, and maybe that could give you like a
that would totally be the next step to get to a better answer to this behavior.
So, how do you handle the NUMA placement for the JVM? What do you do with the application threads vis-a-vis the infrastructure threads like garbage collector?
Yeah, absolutely. So NUMA placement comes from the external tool that is running that program. So prior to forking the process for the JVM or for the Pony program or for the CAF program, it will then invoke NUMA control and tell it which nodes the process is allowed to run on. Or if CPU offlining is used, then we, prior to running the program, switch off all of the CPUs, and then, for example, turn off the first 5 CPUs or how many CPUs we want to run on, and then run that program. But I would be very interested if there are problems with that approach.
So if you pin the garbage collector threads on the same core as the application threads, of course, that's not what the JVM is designed for. So that's problematic.
Absolutely, I do understand. So for running those programs, we didn't make any tweaking to the runtime systems. So we didn't tweak the Pony runtime. We didn't tweak any of the C++ stuff or the JVM stuff. The only thing that we actually did is running on many cores, and in our setup, we were increasing the core count linearly, essentially.
So for the JVM, would the better setting be to leave out this NUMA control that Sebastian has in his benchmark program and just use the NUMA aware flag to the JVM instead?
You probably would see different numbers.
Yeah.
Different behavior. So one could then go further and then call Java native interface also run a set to pin the specific actor threads to the core, so that you still get more control to some degree. But touching the garbage collection threads and the other threads in the system is probably going to be very negative for benchmark performance.
Right. So essentially, like pin the thread pool that's servicing the actors to one socket, but then let the JVM roam free with the GC threads.
What I just wanted to add is that the JVM should actually probably have something built into it already that's sort of handling the NUMA specific problems. So kind of manually tweaking those in the same way you tweak those for more natively implemented frameworks could lead to like really weird results.
Absolutely, I agree. Yeah. So let's continue with the story. And I want to just mention quickly one of the other micro benchmarks, which was just a tree-based Fibonacci number computation. So the benchmark is quickly explained what it does. Every actor in the system forks 2 other children actors, which computed 2 predecessors for the Fibonacci number they need in order to compute the next Fibonacci number. So what immediately comes to mind, depending on the nth Fibonacci number that is going to be computed, that tree is going to be rather large, and it'll probably look something like an actor allocation benchmark. So what we do see here, we have definitely the common stuff. We see that we have some slight improvement from 1 to 2 cores. That's explainable. Because I think it's true for CAF, and it's definitely true for Pony, is that invoking an actor constructor is sending a message. So since we have 2 actors that are being created at a time, it makes sense that it improves slightly from 1 to 2 cores. And then we see some steady improvement for CAF, especially when hyperthreading kicks in. I think that would be due to the fact that the Fibonacci actors themselves are not very busy on their own. There is a question?
Which Fibonacci number are you computing?
Index 35, so the 35th Fibonacci.
Okay, got it.
Yeah. So that you can imagine that would generate a giant tree or sort of giant tree if you were put that into a binary tree. And the interesting bit that we see here is that we have some drastic improvement on ACA for up to 8 cores, roughly, and then sort of we see that it hits the wall and doesn't scale anymore. Now, we have just now looked at very simple benchmarks from the micro categorization, and I found myself in a place where I realized it isn't as easy as I thought it would be when I started implementing that tool chain and run those benchmarks. And the next one is very interesting, and let's get a little bit more technical here. Now, this is a very simple benchmark where you have a producer actor. So that's Pony code. You have an increment constructor here, and it will just loop messages many times and send an increment message to a counter actor. And after having sent all those increment messages, the counter will ask the producer will ask the counter to get the value that it has summed up, and then the counter would just increment its internal counter by receiving that message, and later on tell the result to the producer. Now I have a question for the audience. What do you think the performance graph would look like? And I think in that particular instance we were sending 1 million messages, I think. So it's 1 million increment messages to the counter. What is the expected performance graph?
Don't know enough about actors, but is the counter shared? Like every actor will increment the same counter?
No, so the counter actor is an asynchronous active object, and you send a message to it. So every increment you see here from counter.increment will place a message into the message queue of that actor, and that will be popped off that queue eventually.
It does sound like a bottleneck. So scalability would probably be affected to a large extent.
Absolutely. And what you definitely see here that you definitely have a situation in that benchmark where you have the producer send lots of increment messages onto the queue of the counter, and the counter will at some point in time try to pop off messages off that queue. So I thought this benchmark should look something that would probably flatline, because the mailbox is contended here, and there are only 2 actors involved, so there's no more concurrency on that queue. This is what it looks like. Now what's interesting here, all of them look weird. So I have a theory. I have no idea what's going on. I started to look at this for quite some time, and then I started to realize maybe the issue here is that we have a timing issue on the head of the message queue from the counter actor. Because what can happen here if you have 2 cores or more is that the counter will compete for the head of its queue, while the producer will compete for that originally empty queue as well.
Just a methodology question. How many data points do you have per core measurement?
I think it was, we ran the measurement 20 times on every core and then took the median.
Okay. So the numbers we see are reasonably reliable?
The numbers are definitely reasonably reliable. We did some testing where we had 100 iterations and it looked almost the same. And then we stopped doing those 100 iterations because for some of those benchmarks on such a large box, running those would take rather long. And that's why we limited it to 20, but the numbers are fairly reliable.
Sorry, I have another methodological question. For the JVM, did you actually consider jittering effects? Did you warm up your benchmark in any way before running the 20 iterations? Because I mean, not for this one. This is weird altogether. But for the other one, which was spiking, maybe there was some compilation. Maybe there were some compilation effects.
So absolutely. That's definitely a good point. You always hear in the context of benchmarking that JVM warm-up does make a difference. What we did in the original implementation of that tool, of the tool chain we're having, that it did run the JVM benchmark multiple times and then ditched the outliers of those runs. That is some sort of warm-up, but it didn't really make much of a difference for the behavior for most of those programs.
The messages, so as I understand the benchmark, there's a lot of messages that get created and a lot of messages that get destroyed at all times.
Yep.
So we're doing a lot of memory shifting around and garbage collection, presumably, and so on. Did you look into like that behavior on any of the systems? I don't know whether what Pony does, whether that's garbage collected as well, but yeah. So did you look into the behavior by any chance?
So yes, Pony is garbage collected as well. We didn't look into closer into the GC or memory allocation or freeing in that point. We made an extension to the tool chain that we can have a look at allocations and destruction with Valgrind and stuff. So we're definitely aware of that this is another dimension we need to include into the discussion, but we haven't done that yet. That's the next step.
So I was wondering if it would make sense to actually run these things also on like a single socket machine, right? Because the variation here is like essentially it suddenly gets double, it takes twice as much time and so on. And so,
yep.
And obviously if you know, for some reason you end up accessing memory which is close to, you know, a different socket, then, well, clearly the latency will increase a lot. So
absolutely. Absolutely. So I think the problem will probably be around the fact that you have lots of quick path interconnect communication for this specific benchmark here, we do have a setup now where we have a single socket machine where we run that stuff on, and we'll see how the plots will look like. But I would guess it will be less jitter on that box.
Sorry. Still got the mic. Last comment on methodology from me. You're probably familiar with their work, but these graphs, they remind me a little bit of, I think it was 2 years ago, at Uppsala, Laurie Tratt and his team, they've published this paper on basically evaluating warm-up sequences for various languages, various implementations of those languages. And they remind me of their graphs because they also at some point didn't know what was going on at all.
Yeah.
If again, I don't know if and how intimately you're familiar with their work, but they've done a lot of work into like making sure that, you know, external artifacts do not affect their measurements, and, you know, like even including like CPU temperature and things like that. So maybe worth looking into if you haven't sort of looked into that work in depth, because there may be suggestions on what to do in order to eliminate some of the sources of non-determinism that you might be seeing. Yeah, it's just a comment.
Absolutely, you're absolutely right, and I think that's great input. So originally, when we started with the benchmarking stuff, we definitely wanted to avoid that we run individual programs and just compare them to each other. What we wanted to have is to get a more abstract picture of the actual world in that case. So we're definitely not here in the case for competing stuff. There's another question, yes.
I just noticed that the Pony and the CAF benchmarks, they're both flatlining, but Pony starts getting spiky just before 32, and CAF starts getting spiky just before 64. Is that a coincidence, or is there something?
That appears to be a coincidence. Okay. So there's no hyperthreading involved here, so it appears to be coincidental in that case. So I did some more experiments, but I'm probably going to skip on those. So I thought I could just change the benchmark in some ways that it would behave differently by making either the producer or the counter busy, but just busy waiting so that you remove the contention on the message queue. That sort of turned out to be not really true. It continues to behave weirdly. Now, there is this section on concurrency, and we have lots more programs that have been... Yes, there is a question.
Just one more quick question. So one burning question just for the general thing is, how do you treat the language differences between the languages? So one thing I could imagine that's going on here is, for instance, termination. So if I look at the Arca version, for instance, there's just brutal termination of the whole system after the thing is done. Pony seems to be a more reasonable actor language where you probably can't do that. So you have probably to introduce some kind of extra messaging for termination. How do you deal with that?
So absolutely, you are absolutely right that especially for ACA and even for CAF, there is termination passes involved, and they will be counted because the benchmark runner of those languages would take them into account until the main actor has been terminated. For Pony, what we don't do that. Pony has automatic termination detection. It is based on quiescence, and it will then terminate the program. Now we could change this situation if we were running the time the process needed to terminate, rather than until you get the answer of the program. We are aware of that difference, and we have seen some benchmarks that if you took the time being measured for the process, you'll see some differences, especially for Pony when you have to collect large actor cycles at the end of the program, which arguably you can turn off because you know the program is going to terminate, but that's sort of a situation of flavor on what you're doing here. So let me glimpse over those concurrency and parallelism benchmarks a little bit, because there are definitely some benchmarks where you can find explanations. Now, probably most of you are familiar with the dining philosopher's problem. It's a program, or it's an algorithm where you have philosophers sitting around on a table, and they ask a central entity that they are hungry and that they want to eat, and that central entity will hand out forks, and those forks will be given around in a circle, and every dining philosopher, so only half of the dining philosophers can eat at any time. Now, this is a classic concurrency benchmark because the arbiter that will decide on the philosopher's eating will be contended, and that's why you wouldn't expect to see any scaling. And the good news is that we see similar behaviors as we have seen on the other micro benchmarks we have seen so far. So we have the penalty on 1 to 2 core transition, and we do see some cost on hyperthreading as well. Hyperthreading is something that we do tend to see consistently, but there are even benchmarks where hyperthreading is obviously helping, because for some stuff it's just a good idea. Now, what was an interesting one was the producer-consumer concurrency benchmark with a bounded buffer, which essentially just is a program where data is written and read to from a bounded buffer by multiple entities. What is weird about this graph is that it looks like a parallelism benchmark, because you see some nice scaling and some weird behavior on Pony and hyperthreading. Now, when you look at the benchmark implementation closely, you realize that the bounded buffer is the contended entity, and the difference between bounded buffer and the dining philosopher's benchmark, as we saw, is that the producer and consumer have an item processor which makes them busy. So there's artificially made less contention on the bounded buffer. But algorithmically, it looks pretty much like dining philosophers. That made us think whether this benchmark is pretty much the same. So if you make the philosophers now busy, the shape is almost the same as bounded buffer. And this got me into thinking whether those categorizations are true in all of the situations, and whether most of those programs are actually measuring the same characteristics under the hood. So it probably needs to be that there needs to be some more work to make this a real actor benchmark, because you can do slight modifications to most of those benchmarks, and we have shown that for other stuff that they absolutely behave the same, which is quite unfortunate.
So just to be sure that I understand, the bounded buffer in this case would be, the dining philosophers would be an arbitrator with actors around which are given permission to use forks.
Yeah.
The bounded buffer in this case would be one producer, one consumer, and something in between?
So it's multiple producers and multiple consumers, and the central entity decides on which of the consumer is available to consume a produced value from some producer.
Okay, and
so it pretty much plays the role as the arbiter did for dining philosophers, with the difference that the producer and consumers are busy.
Okay.
And not sending any messages sometimes in between.
Could you back up to the previous slide in that case where?
Absolutely.
There we go. And the one before? Thank you.
Mm-hmm. Now, I want to just show a quick example, which is a true parallel benchmark. So we have a classic divide and conquer situation, which is a recursive matrix multiplication. And what it does, it multiplies two matrices and prints the result in a result matrix. And now the interesting thing is that we see quite some difference between ACA, CAF, and Pony. Pony seems to be at a disadvantage here. Now this is one of those benchmarks where we do see that a language feature makes a difference for performance. And since we do enforce no shared state in Pony, we cannot write concurrently to the shared data structure, which is the result matrix. We know it would be safe to do so because each individual worker in that matrix multiplication is working on its own chunk or own window of that result matrix. We can't do that in Pony so far, so we have to have an additional collector actor which will collect all of the results by sending messages. And then that's why we see a performance disadvantage here. Interestingly, it seems to wash out around the point where we have as many cores as worker actors existing in the system. Now, what are the observations we made from those benchmark runs? First of all, we see jitter, especially on the large box. We do see that hyperthreading kicks in inconveniently for some of those benchmarks, especially when those workers are not busy. We have seen 1 to 2 core improvement stuff. We know that this is due to thread contention on some of the runtime decisions taken. We did see the big variations on behavior busyness, and we have shown that we can make that program easily look like a parallel one. There's a question, yes?
Can I be audience and ask whether you have got any overall conclusions over which languages behave better?
Absolutely. So I can let me just continue to those stuff. So what I definitely found useful running that benchmark suite is that I can just combine all of the information into combined plots for each of those categories. So for all of the micro benchmarks, for all of the concurrency benchmarks, and for all of the parallel benchmarks, and this is what it looks like. So if you combine all of the stuff into one plot, you at least get an idea in which of the categories those languages seem to perform well.
Did you think about, so what I see here in the plots is that, the timeline says milliseconds, right?
Yes.
I mean, of course, it's like, 500, okay, half a second, but still it seems kind of shortish. I mean, they all seem to be somewhat micro benchmarks.
Absolutely.
Even the parallel, the concurrency things. So do you have any thoughts about how a non-micro benchmark could look like, right? Because it's actually difficult to come up with such a thing, right? Given all the different
Exactly, that is an excellent question. And the reason why it's an excellent question is that I found it very hard when I looked at the Savina benchmark suite. I found it very hard, to understand the programs. That take some time, but you can just look at the code and then know how they work. But the difficult bit actually was to make the parameters change in a way that it runs longer, or that runs longer sensibly, so they don't have short-running programs that terminate after a couple of milliseconds. And I found that closely to impossible for some of those benchmarks. So that got me into thinking, because let me just skip over some of those slides to get to some of the stuff we would like to do. Is now from industry, when I tend to implement programs with the actor paradigm, they sometimes look pretty much the same. So what they look like, I have lots of actors. There's lots of communication happening. There are phases of computation. There are phases of just messaging. And I didn't see that for the large majority of the Savina benchmark suite. So what if we could decide to implement, let me just get to the correct slide, to implement a single benchmark to have all of those characteristics we have seen from the Savina suite in one program. And me as a person to use that program would like to fiddle around with the parameters and make it behave as I would like it to behave, rather for computation time, for concurrency reasons, and all of that stuff. So what we came up with is a chat application, and we derived this from the experiences we made programming actor systems in industry. So we think it's a benchmark that maps well to the characteristics of actor applications, at least of how we think about them. And what we have in that benchmark is 4 agents. There is a client, there is a chat, there is a directory, and a login actor, which can be optional. The client is basically someone interested in communication information. The chat is something you would think of as a chat room, and the directory is a layer of indirection for load balancing. So then there is some means of what clients can do. They can do nothing, they can send messages, they can leave a chat, they can log in, they can log out, or they can invite friends to a new chat. and obviously respond to any kind of external events like chat invites, friend requests, logouts, messages, and all that stuff. Now, with the directories and with all of the clients in chat rooms, we do have lots of broadcasting mechanisms where lots of messages are being sent around, where lots of messages are being received, and they can be uniformly distributed. And the question is, can we sort of use this kind of pattern of an actor program? Yes. In order to make some universal benchmark suite with a single program that can be adapted. And I think we can do it with this one. Because we could just make those clients or the chat rooms busy by having lots of computation on reacting to their stuff. We can have fewer directories in a gigantic friend graph so that we have contention on those directories for finding other clients. And that's the main point I'm having here. It fits nicely for distributed computing, so I do want to use that benchmark to run it on thousands of nodes eventually, and I probably cannot do this for most of the Savina benchmark suites because they're so micro that they will terminate until they have been distributed. So that's it from my side, and I would be very happy if we could continue that discussion after the talk, because I think there's lots of stuff to talk about and work on, and I'm here for any questions.